Art. A wonder. Except when it's been compressed and shared 100 times on the web. Ew. JPEG artifacts. That's what that is, right? Well... JPEG. So let's say you've rewritten JPEG for a stupid meme on the internet. I've written a Python script that converts images from an arbitrary format to my new format, JPEG, or Bad Apple JPEG. You can interact with the script through a command line interface running Python, or you can run it in an IDE like PyCharm. First, if we want to compress or encode an image, such as this painting by Monet, we can use this script in the command line. I'm not going to do it because it takes a little bit of time, and I don't want this to drag on longer than it needs to, but you invoke python.exe, wherever that may be located, bapegtool.py, which is our script, in encode mode to start. You put in a transform material, which is a directory full of image files. I'll show you what that looks like in a second. You get a file to operate on, here the picture of the Monet painting, and then a target to put the output in. If I were to actually run this, then what would be outputted is not like a recognizable image format, but a .bapeg file. So I'm going to open this with Notepad, and you're going to see it's not JSON, it's not like a list of things, it is the raw bytes being like printed into this file in order to compress it as efficiently as possible with our JPEG-like compression format. Right? This is very similar to the like glitches that you get if you were to open a JPEG image in Notepad. I could also try opening this in like, I don't know, paint.net or something. Paint.net, just once. It doesn't open. And that's because it is not JPEG, it is not PNG, it is a new file format that its algorithm is similar to JPEG, but in terms of the actual structure of the data, it is not JPEG. You can see here, the gist is, and we will go over more of this in like section 2 when we actually talk about the math behind it. This is the like transform folder that I'm using here. You can see it is every frame of Bad Apple. It's taken down a little bit, but most frames of Bad Apple as individual pictures that can be manipulated by the script. So if we were to actually run this, we get the JPEG file. If we were to run this command, on the other hand, which is the decoding part, using the same JPEG tool, we would get a PNG that shows what the image looks like after having gone through the JPEG compression, which is displayed here. So you can see there's a little bit more noise, the colors aren't quite as nice, the figures are kind of difficult to discern, the brushstrokes aren't as clear, but it is obviously the same image. If I were to run it, I don't have the output because I didn't actually run it and I didn't like save it somewhere, but it went from about 301 kilobytes to 276 kilobytes. It did succeed in compression. It's not as good as JPEG. JPEG can go a lot further because it makes these assumptions and it uses kind of a more general thing that is not like Bad Apple, and you're going to see how Bad Apple is actually used. But it does succeed. Like, it works. It also could be, issues with, like, I'm not putting the data in as efficiently as I could. I am compressing it after writing the data to the file, but maybe there's some other things that actual computer science would be able to figure out that I can't. But that doesn't really matter. As a proof of concept and an artistic or technical demo, this is what we have. In terms of the JPEG file that is outputted by the script that has the compressed file in it, it is the same as JPEG or PNG. The reason that you can't open it by double clicking it and it opens in Photos is Photos does not have a driver or a script that is able to decompress that specific file format. If it came natively with the JPEG tool and it was able to use that, yeah, you'd be able to click on it and then it would just open in whatever application you want. But I haven't set it up to work like that because I don't actually know how you do that. In terms of the actual data, it is contained within that file and it needs to be interpreted by the JPEG tool in order to write or read it. Here are some options that the JPEG tool provides. We've seen mode, transform, file, target. We also have 4 quality related values. So I'm going to go through these briefly one by one, and for some of them I think it'll be more obvious as we go through some examples afterwards. SQ is spatial quality, which is how many layers are stacked on top of one another in each block to recreate the features of the image. If this was 1, you would get a mosaic effect, where it's just or a collage, where it's just the images that are kind of next to one another, right? and it is choosing those images to create your result, but it's going to have very, very low quality. If this was extremely high, then you would get your image out perfectly, and it would be able to perfectly recreate the image with some caveats. TQ is temporal quality. This is an integer, or a type of integer actually, a byte or a half int or a full integer, that is used to select the frames that are used as the material in the transform. That doesn't make a lot of sense, but the reason that it's like this is to preserve compatibility between different transform like videos that you're using to feed into BAPEG tool. That's not a useful thing per se, but it is a really interesting thing to look at, and we're going to see some examples. VQ is value quality. This is an option between types of floating point numbers. This is how nicely to store the color and the brightness of the picture, more or less. If this was really low, the colors won't be as true to the original, but the human eye isn't really as good at picking that up anyway, so it can be pretty much at the lowest setting, and it's not going to mess things up too bad. You can see, like with this example, there is some color issues. The original one is like less green, but if you were to see it, issues of quality relating to the noise that it is introduced by the algorithm is like more of an issue than the color degradation, so it really doesn't matter. Okay, block size is the size of blocks that the image is broken up to in order to process it. If this was 1, then every pixel would be set to be its own color, basically. So it wouldn't do any compression, and it would actually kind of balloon the file size to just like ridiculous amount. If it's the size of the image, and it can be up to 255. So if you had a 255 by 255 pixel image, then it could be the size of the image. You would be solving the image globally, and we're actually going to see what that looks like in a second. First, if spatial quality is 1, you get this mosaic effect, like I said. It's kind of like those Bad Apple, but it's made of Bad Apple videos, where the silhouette is made up of other frames of Bad Apple that are positioned next to one another in order to make the black spots overlap to make this like overarching silhouette. So you can see that BAPEG like has to change the average color of each frame as it stacks it onto the image. That's just necessary in the algorithm. That's just how it works. So you don't get exactly the same mosaic effect, but it's more or less the same. And you can see how like doing this, we have thinner frames here where there's only some data on like the left or on the right side. You know, it is choosing them intelligently in order to create the image that we want. If instead we were to set the block size to the entire image and give it tons and tons of layers to stack on top of one another, we would get something like this. This starts with 1 or 2 layers, but then it increases substantially. Oh. The quality, I don't actually know if this is going to be any better like through the YouTube video, but let me pull that up on my computer so the quality is a lot better. It is in single images, JPEG, images, mini video 2. Okay. So yeah, it starts with a couple, and then it keeps layering more and more on, and eventually the figure in the background starts showing through. Just by changing the like opacity and layering of the frames that are stacked on top of one another. This is exactly the same thing that was used in my Steamboat Willie video. So this is kind of an explanation of that in some ways. And this is a tool that you could use if you wanted to recreate that video. Although, if you wanted to do that, you probably want to like rewrite the tool anyway. Okay, this is really interesting. So this is like one of the interesting effects that can happen when we we use that timestamp thing that I was talking about. So what we can do is this original picture, the BAPEG file that we made was encoded using Bad Apple here, right? Because I was working on the Steamboat Willie video, I have the Steamboat Willie frames also in a big folder on my computer. So if we were to decode it using Steamboat Willie, suddenly a lot of the information isn't useful anymore. And instead, the picture, like all the features kind of melt away because Steamboat Willie has really low contrast, which means that the values that are used for Bad Apple are way too low to actually affect Steamboat Willie in any way. And anyways, the frames are not chosen intelligently anymore. So the only thing that comes through is the average sort of color, which is the color of each like block. So we get a pixelated effect with a little bit of grainy noise sort of thrown in the middle of each frame. If instead we were to encode the image with Steamboat Willie and decode it with Steamboat Willie, these are pictures from Steamboat Willie, I'll come back to this in a second for something interesting to point out though, we get a perfectly fine recreation. This looks really similar to the one that we did when we encoded and decoded with Bad Apple. That's just because as long as the transforms match, it's able to find a good solution to the image, more or less. It's just when you mix the transforms that suddenly a lot of information is thrown away because it is not like necessary or relevant anymore. It doesn't actually apply to this specific image. you can see there are some differences in when you choose the transform. So for example, Steamboat Willie, some of the images have this vignette effect on the corners and kind of the edges. It's more prominent in some frames than others. But what that does is all the images have really similar edges, which means that the program doesn't have a lot of variation to operate on with respect to the edges for each block. So I don't know if it's visible with the YouTube compression and everything. If you were to download this image, you would be able to see that each block has a little bit of an outline around it. It does not connect to its neighbor blocks very well because of this vignette effect where the program cannot actually vary the edges of the block very much because they're all very similar. Now that we have a JPEG file that is encoded with Steamboat Willie, we can decode it with Bad Apple. It's the flip of what we did for the really pixelated one, and we get sort of the opposite of that. It's a crazy, absolutely insane looking mosaic where the comparatively very strong values that we need to encode Steamboat Willie are pasted onto Bad Apple, and suddenly they're blown way out of proportion, and we get these crazy colors and like whites and blacks and really insane values that cannot be rendered properly. So again, the blocks are kind of broken up, they don't flow into one another because it's just like full of garbage data. But I think it makes a really interesting and weird looking mosaic. Okay. What we can do, instead of using something like Steamboat Willie or Bad Apple or like a video that was made for people, we can use the discrete cosine transform, which is the transform that JPEG actually uses. So if we use that, which here's examples of like the symbols or the individual layers that the discrete cosine transform uses if you were to turn them into images. There are 64 in total, but you can see that they're more like they are optimized for encoding videos basically, or like signal processing instead of being good looking for a human being to watch. You can also change the block size to be like what JPEG actually is, which is 8 pixels by 8 pixels for each block, and we get a very nice picture after decoding it. And that's because JPEG is designed for encoding and decoding, so we get a better result anyways. Unfortunately, JPEG does not do compression anymore if you do this, because suddenly all the data that JPEG is able to throw out, because it makes the assumption that you're using JPEG for every step of the process, we can't make that assumption anymore, so we're just carrying tons of extra data, and it isn't really compressing anymore. But again, this is a technical thing, and it is just showing that JPEG is a quality of JPEG if you were to give it the right inputs, more or less. So that's the extent of the JPEG tool. If you want to play around with this yourself, you will be able to find the Python script in the description along with some example JPEG images. I'm not gonna like share the entire project that I have that's working on because there's just tons of junk in there that is used for debugging or testing or like the decompiled frames of Bad Apple or Steamboat Willie that you don't need like gigabytes of stuff on your computer when you could download that yourself, and you probably don't even want to use that. But if you are comfortable, like if you know how to use a command line or you can do some Python programming, you will be able to open this up, see all my comments, and figure out how the algorithm works and use it yourself, I think. Or if there's interest, maybe I'll make like a more user-friendly version in the future. I don't know. This is more of a tech demo and an explanation. So, as for the JPEG tool, that's everything there. Now we're going to move on to the math section. Section 2, how JPEG or JPEG works. This is going to have to get a little mathy. Not in the sense of numbers or arithmetic, but in how we're going to need to get abstract to understand the fundamentals of JPEG and beyond. We're talking about linear algebra here, a study all about manipulating vectors in space. I had the first layered frames related idea after taking a linear algebra class, and I think that after we run through the basics of vectors and spaces, it's going to really tie the whole concept together and allow you to begin exploring new ideas too. So, first we need to run through some basic ideas in linear algebra, and ultimately I want to cover each of these bullet points here, just that we have kind of a basis of vocabulary to talk about when we're discussing this sort of thing. Linear algebra is a field of mathematics that is only focused on operations that behave linearly. Specifically, linearity is related to additivity and homogeneity, but for the purposes of this video, that really isn't super important. The fundamental elements of linear algebra are vectors and matrices, which generally introduces a new method of solving systems of equations, but really it's like much more profound. So, next up, vectors. Vectors are really the most important part of what we're looking at here. A vector can be just about anything. It could be a collection of numbers, or a function, or like the state of a system. And by calling an object a vector, it helps us apply mathematical knowledge to discover new things about it. Like, we could apply algorithms to it, or we could say things about how it could change over time, or things like that. A really simple example of vectors are position vectors. Position vectors are often described as arrows that point from one location to another, or points in space. You can see that in this example, a position vector is really just two numbers or components. So here I have a position vector called u. Let me set this scalar to 1. And it is this blue line here that has a draggable little point at the end. So I'm defining u as 2 points here, which are a horizontal displacement of 1 along the horizontal number line, and a vertical displacement of 0. No movement along the vertical number line. Notice how, if I wanted to, I could change these values. I could set 1 to be 2, and that's going to change the location of the end of the vector in space. Changing the horizontal position vector value does not change the vertical displacement value at all, right? Or vice versa. If I set the vertical one to be 2, it's still moving horizontally by 2 because that's what I set it to be. Or if I set this to be 5, the horizontal displacement is still 2. So let me set this back. Okay. Also, note how this vector could be described as having a direction and a magnitude, or length. If I multiply the position vector by a number, it scales the vector, the magnitude changes, which here I have that tied to a. I could set a to be 2, and then now the length of the vector has changed, but its direction along the number line has not changed. I have this draggable, so I can just grab this and it'll automatically change a, and this will give us an idea of how we could scale this vector. But no matter where I try dragging a with the cursor, it won't change the direction of the vector. Scaling it only changes its magnitude. Like scaling the vector by different amounts. I can scale it so it touches different points. It could actually touch an infinite number of points, right? For every point, I could touch halfway in between those 2 points. So we have an infinite number of points here that we can touch by scaling the vector. In total, the complete set of points that this vector can touch if I wanted to scale it to any arbitrary value is the line that is along the direction of the vector. So I have that here as this dotted line. You can see it's the whole horizontal number line for this particular vector. I can't make it touch points that aren't on this line, because that would require me to change the vector's direction, which a scalar can't do. If we disregard the vector's original length and we're just looking at this line, or the set of all points that a vector can touch if it's scaled, this is called the vector's span, and it's really important as a concept. I will add a second position vector so we can see how they interact. These vectors each represent movement from one point to another, so I can just add them together by moving along the first, and then from the end of the first, moving along the second. So here's the sum of them. I have this here, which shows you could trace this purple arrow by either adding the components together. So the components of this purple line are the first part of u times its scalar plus the second part of v, or the first part of v times its scalar. Basically, we're just adding the horizontal displacement and the vertical displacement. Or you can think of it as moving along the vector v, the red one, and then moving around the blue one, the vector u. So if I were to keep these separate and scale them, you can see that changes the sum. I can change u, and that makes the sum sort of move in the direction of u. I can change v, that makes the sum move in the direction of v. If we do scale them individually, we'll see that something interesting happens. By changing these scalars, I can touch every point in the 2D plane. So if I decided to touch 3, 2, I could do that by, I'll move this a little bit here, and then I'll move that one back, and there we go, 3, 2, right? Or if I wanted any other point, I could set these so that I am able to get there. There's no limits there. If we consider both vectors as tools in a set, the span of both combined is not a line anymore, but it's the entire 2D plane, because I can touch any point in the 2D plane. I can also add a third vector. So we have u, we have v, now we have w. This is really long for some reason. It's in a different direction than the other two. And if I were to create a sum from all those, u plus v plus w, this black vector, I can still change its position by changing the individual vectors, their scalars that are associated with each of them. But it won't change the span. Instead, this third vector is kind of redundant. If I wanted to touch 3, 2 again, I could do that like this maybe. Or I could set one of these to be something else. I could set the red vector has to be at this point here, 2, 2, and I can still get to the point that I want to touch by manipulating the other vectors. If I wanted to, I could position the original 2 vectors in order to totally delete the new vector. So for example, if the new vector was going to be set at that position there, whatever that is, the green one, I can manipulate the other 2 so the result totally deletes it, and we get back to 0. There we go, like that. That ability, being able to negate one vector in the set using non-zero coefficients in the other vectors, makes this set of vectors linearly dependent, as like a vocabulary term. Whereas with only 2 vectors, they were linearly independent, because there wasn't any redundancy for spanning 2D space. There is a way to have only 2 vectors, but for them to still be linearly dependent, though. If these 2 vectors have the same direction, so for example, let me hide these. If we start with u again, it's horizontal vector, and then if I add f, which is also horizontal, of a different color, now we don't actually have any new information in our toolbox. Since we don't care about the vector's magnitude, or their length, we only care about the direction. These 2 vectors have the same direction, so we're not really adding anything by adding the second vector. You can see that with the 2 vectors in the same direction, the sum, u plus f, is still constrained to be along the horizontal number line. I can move these around any way that I want, but it's not possible for me to touch points that are outside of the horizontal number line just by scaling the 2 component vectors in our sum. That means that this set of 2 vectors, u and f, are linearly dependent, even though they're in 2D space and there are 2 vectors. So they need to have different direction in order to be linearly independent. Maybe from that you can figure out what 2D or 2-dimensional actually means. It actually refers to our set of vectors. The plane here is 2-dimensional because it requires 2 linearly independent vectors if you want to be able to touch every point. The dimension of a space is the number of linearly independent vectors required to span the entire space. And it doesn't just have to be a 2D grid or a 3D space. Our space could be basically any situation where you have objects with vectorish properties. And we're going to see that come into play when we talk about images again in just a second. The set of vectors that do fulfill that criteria, they're linearly independent and they span the entire space, are called a basis for the space. And there isn't just one basis per space. There could be many options for a basis, but usually mathematicians decide on one to be the space's canonical basis for ease of communication. In a positional sort of space like this 2D grid, this is represented usually by the axes. So I'm going to hide these. But if you think about it, I defined u to be 1, 0. Like, what does that actually mean? What it really is doing is it's 1 times the unit vector, or like the basis vector that's in the horizontal direction, whatever we decide that to be, and 0 times the basis vector that's in the vertical direction. Not really important, but just kind of an interesting thing to think about. Alright, we're almost done with the totally abstract stuff. Just note this. A basis, a set of linearly independent vectors that spans a space, can be used to create any vector in the space by scaling each basis vector and adding them together. Like how we can scale and add the 2 vectors in the example to touch any point in 2D space. That's how all of this works. Alright, now we're going to talk about images, finally. Images can be vectors too. So, if we had this image here in this file, each of these layers is going to represent a different vector that we're going to be talking about. But you could kind of imagine this as like a list of numbers or booleans or whatever. This is off or 0, 0, 0, 0, 0, blah, 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 1, 0, 0, 0, 0. It's just a different way of representing the data that is really just a sequence of numbers. So, they can be vectors too. You can scale them and layer 2 images on top of one another to add them together. So for example, if I have each of these layers as a separate image, I can change the opacity and layer them to add them together. Like, let me introduce here. You can see that if I go into settings, we have this opacity value, which is what I'll be changing. This is sort of our scalar for each vector. And the blend mode is additive, which means that it's going to sum together the components or the pixels in each of these vector images. So if I were to turn on another layer, that would add the 2 layers together, and we'd see the result in this center screen. Turn that on. The second layer has another pixel that's on. If I turn both of them on, wow, both pixels are on, right? and I can change the opacity in order to sort of scale that. So I can lower the opacity, and it goes from the first vector to the sum with a linear coefficient there. I set that to maximum. You'll note that even though I have these vectors and I can add them together and everything, the final image that I get out of the process is still limited. It's basically just going to be like a black and white blob. And in the end, there's a range that we can reach using these vectors or these images as what we're constructing our final image with. I can't just make any image because this collection of images here doesn't span the full range of images. And let me turn all of these on. If I constrain myself to making images using just by turning on or off these layers, I can make a good number of different images, right? I could make something like that, I could make something else, but I'm still limited to what is available in these layers in order to make new images. If you count, this image and each of these are 8 pixel by 8 pixel images. Each pixel is totally separate, if we were just drawing them ourselves, from the neighboring pixels. Setting one pixel using like the pencil tool or something to be white and another one to be black doesn't affect its neighbors at all. So each of these is sort of a separate dimension in the space, bringing in some of the vocabulary that we just learned. It might be kind of difficult to conceptualize, but if you think about if we had a lot of these layers and we had one for every pixel in the image, then we would be able to recreate any image just by changing the opacities of all of these layers. What that means is this is a 64-dimensional space. And that, I mean, 8 pixels times 8 pixels, 8 times 8 is 64. Like, that's what the connection is. Because the pixels are independent, that's why we have a 64-pixel image as a 64-dimensional space. That means if you did want to create any image by scaling and summing a set of vector images, we would need a linearly independent basis of 64 different images. It is a vector space, so if we want a basis, we need to have the number of vectors that is the same as the dimension of the space, and they all need to be linearly independent. That exactly would allow us to span the space of 8 by 8 pixel images. So JPEG uses these images that we showed earlier, right? These are 8 pixel by 8 pixel, and a fun property, these are like made from cosine waves. A fun property of cosine waves is that waves of different frequency are like independent from one another. So each of these images have a different vertical and horizontal frequency that's sort of going on, which means that each of these, barring anything else, this set is like guaranteed to be linearly independent. And it's very easy to construct this linearly independent set, which is why they choose this one. Another reason why they choose this particular pattern is that it goes from like super low detail, big moves, big swing patterns at the top and kind of to the left. And then at the bottom right, it's only the fine details. So if they were to encode the image using this basis, instead of saying the color of each individual pixel, they just say the coefficient that's associated with each of these vectors. And that means that then they've separated out the big details from the small details just by transforming it into a different basis, but it's the same information. So then if they just get rid of the high frequency, like the fine detail stuff, by just kind of ignoring what the coefficients are for this corner of the image, the bottom right corner, then they know that from like psychology and biology that humans aren't as good at picking that kind of information up. So just by dropping that, instead of doing something dumb like just ignoring certain pixels in the image, they are discarding only the information that would not be very efficiently picked up by the human visual system by changing the basis from the basis of individual pixels into the basis of the cosine transform, so that they're able to select the high detail stuff like really easily and drop it. So that's the gist of why they do that. JPEG doesn't have the advantage of knowing which basis vectors or which images in its transform have fine detail or not, so it isn't as efficient as JPEG. Like, JPEG is doing this is very, very intelligent as a way of compressing information. JPEG is just kind of doing it for kicks, so we don't have that advantage. Instead of using boring wave functions in the basis, JPEG allows you to introduce your own images, such as the frames of a video, to substitute as the basis of the transform. Obviously, any generic video probably isn't going to have the perfect characteristics to be exactly a basis, right? If you just pick 64 random frames in a video, it's really unlikely that they're all going to be linearly independent. I can go to my bad apple frames, and we can look if my, like, the part of the 64 random frames that I picked, knowing that I need 64 total, were these two images. These look really, really similar. They're not exactly the same, like, they're different, but they're similar enough that there's probably a lot of overlap, and you're gonna have to do, like, a lot of finagling to separate it out, the difference between these two. Really similar vectors in your basis, they could be linearly independent, but if they're only like a little, like just barely linearly independent, then you're gonna have really huge coefficients in order to manipulate them properly, and that's kind of bad for the information retention. So instead of picking 64 random vectors, we basically just use the entire space, and we can let these very clever algorithms and procedures that mathematicians have created, and they'll just decide like which ones are the most important, right? What that actually looks like is knowing that each image is just a sequence of numbers that is displayed differently. We can literally like reshape it into a really, really tall, like mathematical vector, like a tuple or position vector, where it's just a series of numbers that are packaged together. Then we put that into a matrix, and if we know what our target frame is that we're trying to replicate using this like basis, we can use a matrix equation called the normal equation to just solve for that, and it'll get as close as it can automatically, and you'll get like the mathematically like perfect optimal solution. And that's really good, except if you have really, really large matrices, like for example if you were to flatten down an entire huge massive image into like a column vector and then stack tons and tons of them together to make a matrix, that takes a really long time. So in the Steamboat Willie video, I use this normal equation related stuff of just pure straight matrix math. For JPEG, instead of using that, I'm using a algorithm I found called the orthogonal magic pursuit that does basically the same thing. It's a little bit worse, but it's a lot faster, and that's really what matters. Again, this is a demo and kind of an idea that I'm floating instead of like trying to be mathematically perfect. So if you want to see exactly how that's implemented, the Python file is again going to be in the description. You can poke around in it. It's like, you know, you can access the algorithm in SciPy, and you just call it, and it works as long as you have everything set up in matrices and vectors using NumPy like you expect. There's a little bit of an explanation for how all this works. I've been kind of awed by the attention that the Steamboat Willie video got, and I loved most of all the comments that showed genuine interest in the math behind the process, which informed my secret agenda for this video, which was to teach you linear algebra. Hopefully, I've informed you about something that I think is really cool and how applying math in new ways can create something kind of beautiful, or at least, you know, interesting enough for like 20 minutes. I aim to never make another video again, but I've had a lot of fun making this one, honestly, so it's highly likely that I fail, and you'll be seeing more of me if you follow this channel. To help me reach my goal, remember to dislike and unsubscribe and only watch videos if they add material value to your life. Peace.